Hello. So, I will give a short talk on how to train GANs. I mean, I've explained that GANs are not very stable. So, these are some tricks to help you train GANs a bit more stable, but these tricks are not grounded in any theory. It is just tricks that many people have found to be useful. This will be a short, maybe 20 minutes, and then I will talk about PyTorch, which is a framework that I developed. Okay, to start, GANs are not stable. They're like a pack of cards. You never know when they will stop working. So, in terms of the stability of GANs, the original paper on GANs was in 2014. That's kind of how the samples looked like. And then in 2015, we published LabGAN, where the samples look like this. What we did was we improved the model architecture, and we were still doing visual inspection. It's like, oh, can we tell whether the model is working or not? And then we had a lot of hacks trying to stabilize, and some of it was just luck. We tried things and it worked. And then with DCGAN, many hours of trying to find stable models. Finally, we got it to be stable up to 64 by 64, but there's still a lot of more dropping and underfitting. And then later in 2015, or I think 2016, Tim Salbans and his team at OpenAI, they published a few more hacks where you just have more heuristics on how to stabilize GANs. And these were the pictures they got from ImageNet, which were supposed to be dogs, I think. And in 2016, 2017, there were many papers that came with the same conclusion that said regularize the norm of the gradient of your GAN training. And then one interesting repository that I saw was someone implemented all the GANs of different kinds, and then they just compared them arbitrarily. Like, when you're writing a paper, you take the best results and you ignore the worst results. But someone independently, they just implemented everything and they just tried everything out. And the result was that most GANs were still not working very stably across many data sets. Now let's compare the training of GANs to training supervised classifiers, let's say standard convolutional neural networks. Then in standard connets, generally, like, whatever you try, it sort of works. It will give you some decent accuracy. And you know that if your loss goes down, your validation loss goes down, you know your training is working. But in GANs, it's just like, okay, let's try this. If it produces a better quality image, it must be better. It's very unprincipled. So saying that, let me start with, I think, 14 tricks on training GANs. First, normalize the inputs. If you have an input, make sure it's mean normalized and has a standard deviation of 1. if you have a generator, make sure the last layer of the generator is bounded so that it can produce outputs between -1 and 1. That's just good practice, not just for GANs, but for any scenario. And then the second trick is if you're using the classic GAN formulation, then in the paper it's usually people write min log 1 minus d, but practically you just use max log of d. In the original paper, they actually mention this particular formulation and say, because this original formulation has vanishing gradient problem, we use this thing. In practice, it's very easy to just flip the labels when you want to train the generator. You just give real labels to fake and fake labels to real. Second, this particular thing only applies to the classic GAN, but there's a lot of new proposed loss functions by many people. I've given some links here on people, someone from GitHub implementing many of these loss functions. The third, if you're using GANs and you want to do interpolations, that is, you want to go from one part of the latent space to another part of the latent space, one of the common things people do is they just take a line between these 2 points. That is generally wrong. It gives you bad results. What you want to do is your sampling of your latent variable is usually from a normal distribution. So it's spherical in nature. So what you want to do is go from one point to another point on the sphere, not on the straight line. So that's just something you should do to get what you want. A lot of people screw this up and they get bad interpolations. The fourth is, if you're using batch norm, try to do different batches for real and different batches for fake. That is, you either give all real samples to your discriminator or all generated samples. Don't mix real and generated, because batch norm has a very strong issue with if you mix real and generated, then the batch statistics are very weird. You're not normalizing your samples either to be better for real or for generated. The fifth is avoid sparse gradients. So if you look at standard neural networks that are commonly used, people use ReLU and people use max pooling a lot. If you use ReLU, then every output that is below 0 has a 0 gradient. And so if you look at your gradient distribution, most of your gradients are 0. That is what I mean by sparse gradients. That is, most of your gradients are 0. Similarly, for max pooling, only the max element in each window has a gradient flowing through. All of the other elements in the window have 0 gradients. Empirically, we've just been seeing that GAN training does not like sparse gradients. If you use leaky ReLU, which has some gradient, whether you're below 0 as well, or if you downsample with some kind of convolution or average pooling, it works much better. The next is soft and noisy labels. So one of the things that was proposed in Tim Salomon's paper, Improved Training of GANs, is that instead of giving a label of 0 for fake and 1 for real, you can give some softness, like your fake label is between 0 and 0.3, some stochastic number, and your real could be between 0.9 and 1.1 or something, and that seems to be a bit more stable. And in terms of which architecture to use, DC-GAN sort of always works. If you can't use DC-GAN, make sure your model's loss is a hybrid loss. That is, it's a GAN plus VAE or a GAN plus least squares loss. And it seems that from the improved WGAN paper, one of the takeaways is that width matters more than depth in GANs in general. If you can make it wider, do it. One of the things that's interesting is actually reinforcement learning and generative adversarial networks have a very close relationship. If you read this paper by David Pfau and Aurel Viñas, they try to make a connection between reinforcement learning and adversarial networks. A lot of the stabilization tricks that you use in reinforcement learning, you can actually use the same in training adversarial networks as well. Things like experience replay. These are common tricks used in RL, and they actually work pretty well for GAN as well. The optimizer, just use Atom. Atom seems to work pretty well for GANs in general. Or RMS prop. RMS prop also works well. Number 10 is multiple papers. I think 3 papers or 4 have concluded that if you add a penalty term that normalizes that clips, make sure the norm of the gradients is within some bound, then the stability is good. Don't try this thing where a lot of people have tried this and failed, where they think, oh, it's a game where you're trying to train the generator and the discriminator, so if I try to make sure the loss of both is equal or there's some equilibrium conditions I find, it's gonna work. Many people have tried it without any principled understanding of what to try, like, oh, I'll try this, I'll try that. If you're just trying to do this without any mathematical motivation, then I would suggest don't, because many people have tried it without a mathematical motivation and it has gone nowhere. Unless you have like a clear understanding of what you're doing, just know that it's a well-tried path and no one has gotten it to work. 12 is something that's a very obvious thing to tell people in unsupervised learning. If you have labels for something, use it. If you have labels for part of your model, then do a conditional generation for that part of your model. And like make sure you use the labels. You always get better results if you use labels. Some papers actually said that if you add noise to your inputs, that is, initially in training, you just add some noise to your inputs. Like, let's say your input is images, you just add lots of Gaussian noise that the inputs look very, very noisy. That actually helps because then the generator, then the discriminator can somewhat not discriminate very easily between the real samples and the generated samples, and over time, over training, slowly reduce the noise in the inputs. The 14th trick is train the discriminator more. If you do one generator iteration, do multiple discriminator iterations. These both papers, WGAN and WGAN GP, suggest 5 times discriminator iterations for one generator iteration. And you can't really cheat by just increasing the learning rate of the discriminator 5 times, because um, your gradient only applies to a neighborhood of linearity, and it's actually like just cranking up the discriminative learning rate is not equivalent. 15, avoid discrete spaces. If you have to generate text which is doing something like every time step I want to generate 1 of 10,000 words. These are discrete spaces. GANs don't work very well for discrete spaces. If you have a generation that has to do some discrete prediction, somehow turn it into a continuous prediction problem with some transformation. As an example, some of my coworkers have published using GANs for doing unsupervised translation for text, and they got it to work because they posed the problem as you predict a rotation matrix from one space to another, and generating this rotation matrix is fairly smooth like space. It's not a discrete choice to make, and that worked. Conditional GANs. If you're doing conditional GANs, here's one trick. If you have discrete conditional variables, like I want to generate a cat or a dog or a boat or something, if you have some kind of categorical inputs, then learn some embeddings for those inputs. That is, the categorical input directly comes into an embedding there. There's some fixed dimensional embedding that is learned, and project that embedding as just a channel in your image. If you have like a 4-channel input for your generator, then add each of these variables as like another X channels, and that seems to be what most papers do, and it seems to be what works. Just a short conclusion. I think this is, with my previous talk, this is not needed. So that's a quick overview of how to train GANs. This is mostly like practical tricks. If you're training GANs, then you can use these tricks. Next, I will talk about PyTorch, which is the framework that I have developed along with my colleagues. Just trying to find the slides. Okay. Okay. Talking about PyTorch, this is actually all the people who have been developing PyTorch, and I think some of you already use PyTorch, and I want to give a shout out to GitHub user Lantha, who is maintaining the TensorBoard integration of PyTorch. He's somewhere here, I don't know where he is. Where is he? Oh, there. Thanks for doing that. So PyTorch, for those of you who don't know, it's a deep learning framework. This is kind of the overview where it is. It's an alternative to NumPy, for example, with GPU support, and it also has an automatic differentiation engine. It has a gradient-based optimization package, like you have several methods like SGD, RMS prop, atom, and so on. And there's some utilities as well. Starting with the NDRA library. So you can think of PyTorch as a replacement for NumPy. Just like in NumPy, there's np.ndra. There's in PyTorch, there's a torch.tensor. There are several hundreds of operations in PyTorch. Linear algebra operations, slicing, indexing, and so on. And there's a very fast acceleration on GPUs. As an example, well, you can't really read the code, but this is an example that's just showing that on the left side is a NumPy program, on the right side is a PyTorch program. It's just very, very, very similar writing either programs. So practically, I'll try to zoom in maybe. Actually, I can't. I don't know how to do that. I hope you can see, but I'm not sure. PyTorch, the way you use it is you go to the website, you install PyTorch with the command that is given, and then you just call import torch, and then you can create a tensor, you can print it, you can create random distributions, and you can print the size of your tensor, and you can do things like indexing, just like NumPy, and you can do mathematical operations like addition. You can, one thing you can do which is convenient is you can convert a PyTorch tensor to a NumPy array very efficiently. The way it works is the underlying memory is shared between the PyTorch tensor and the NumPy array. So doing the conversion is actually a free operation. It's very fast. And the additional advantage is if you actually change the PyTorch tensor, then the NumPy array is also changed, and vice versa, because they're basically sharing the memory in their internal. So similarly, you can do the other way as well. You can take a NumPy array and you can convert it to a PyTorch tensor. Again, it's a fairly cheap, almost free operation. And if you want to use NVIDIA GPUs, you can just call .CUDA on a tensor, and it will automatically be converted to CUDA. And then any operation you do on this particular tensor will be done on the GPU. So when you call .CUDA, the tensor memory is moved over from the CPU over to the GPU memory. And any subsequent operations are done on the GPU. Coming to the next part, we have an automatic differentiation engine, which is very useful if you're doing neural networks or reinforcement learning and so on. What we have centrally is we have one thing called a variable, which is just a small wrapper around tensor. So here, for example, I'm creating four randomized tensors, and then I'm putting them inside this class called variable. And then any subsequent operations I do on these tensors, they will be recorded in a graph. So if I do something like a matrix multiply, I know that I2H was created by W and H. So H to H was created from the matrix multiply of W and X. So I can do many operations, and automatically a graph is built with how each variable was created. And then you can call backward on some variable and then the gradients with respect to every leaf variable, every orange nodes, will be computed, because you can use this graph and take the chain rule and compute the derivatives of one node with respect to another. So if you want to build neural networks, we actually just add a small abstraction on top of this powerful AutoGrad engine, where I will explain it by example. Here's a small convolutional neural network that is implemented in PyTorch. It is subclassed from nn.module, and it has a constructor where you can specify all of the layers that you want that have learnable weights and so on. And then you have one function that you specify, that is the forward function, that defines how your input goes to your output. So here my input is x. X is going through the convolution layer, and the result of that goes through a max pooling layer, and the result of that goes through a value layer. And similarly, another set of operations, and then I reshape my x, and then I send it through a fully connected layer, and I apply some dropout, and then finally another fully connected layer, and I send it through a log of the softmax operation, and I return. And so my network is defined by this Python function forward. Whatever I write in this forward function is how I define my neural network. And finally, to use my network, I just create an instance of this class, and then I can send an input, which is a variable, through this model, and I will get an output. Next, we have an optimization package. We have a lot of the standard methods that are SGD, AdaGrad, LBFGS, Atom, and so on. And the way you use it is you create a network, and you create an optimizer that gets all the parameters of the network, which are the learnable weights of the network, along with, you can set some learning rate and so on. And then usually you loop over your data set. Let's say there's a supervised learning. You get some input and some target, and you zero the gradient buffers of your optimizer. You send the model through the input through the model, you get some output, you apply some loss function. You call the backward, which computes the gradients of all the parameters. And then you can call optimizer.step, which just does like one optimization step. If it's SGD, for example, you do like x minus learning rate dx. Next, I described what PyTorch is and like what are the inbuilt functions, but I will also now try to describe how PyTorch might be useful to you, whether you're a researcher or you want to do your homeworks or anything. So usually, let me go through how research workflows look like. So let's say you are doing your PhD or your master's here, and you have some idea. You're like, I want to try this new thing. Then you want to try this idea, so you design some experiments. You say, okay, I will pick this particular data set. I will construct my model, or like I will construct my idea, and then I will train my neural network and do some validation, and I will try to publish a paper. And also, you do some literature review as well. So, in practice, what this means is you write data loaders. This is the worst part of doing research. And then you build some models. You write some model definitions. You implement some training loop, and then in case you want to resume from some already trained model, you implement some checkpointing on how to save your model to disk and how to load it back. And you also build some baseline models, and you deal with, if you're doing neural networks, you want to train it on GPUs. And if you don't have data sets, you might be trying to interact with a game or some robot, then you interface with the environments. So my claim is that PyTorch, along with Python, like all of the packages in Python, is one good environment to do this. So coming to writing data loaders. Every data set is different because that's just how it is. And every data set has to be pre-processed differently, normalized differently. And the third thing is, because you're using GPUs frequently, you need an efficient multi-threaded data loader to load samples from disk very fast. One of the solutions we provided with PyTorch is we share the data sets and data loaders across the community. So if you want to load ImageNet, you don't need to sit and write your own ImageNet loader. If you want to use Coco or Cypher or MNIST or SVHN, or there's many more, you don't need to write your own data loader. It's already inbuilt as part of the Torch Vision package. Similarly, if you're doing NLP and you want to load Pen Tree Bank, or if you want to load Wikitext or WMT, there are standard data loaders in the Torch text package for all of these. And another thing is, if your data set comes with a Python interface, then it's very convenient to just use that from PyTorch. As an example, there's this Parlay project from Facebook that defines data sets, data loaders for 20 question answering data sets. And it's very, you can use these all with PyTorch. So in practice, if you want to write your own data set, data loader, the way it looks like is you just create a particular data set object, and you can give some pre-processing, like, okay, I want to do some random image augmentation. And then in this line, in this last two lines here, you take this data set object and you construct a data loader that is a multi-threaded version of this data set that will automatically load the data from these data sets across multiple CPU cores. And this is an example of writing your own data set. If you have to write your own data set, you don't have this data set available in the PyTorch community, then all you have to do is you have to define a constructor with just like options for your data set. You have to define a get item that defines if you want to load the kth element. Let's say you have 10,000 elements in your data set. Your get item has to define how to load some index of the element from the data set and return it. And you have to define a length function that just tells how many samples are there in your data set. It's very simple. It's usually just like a few lines of code. And next, coming to interfacing with environments. Almost every environment these days has a Python interface. So using it with PyTorch is, you don't have to do anything special there. And coming to debugging. So for debugging, PyTorch is a Python extension. So you can just use any of the Python debuggers in PyTorch. For example, this is PyCharm, where you can set breakpoints and you can conveniently debug. You can also add some print statements, and that also works with PyTorch. It doesn't work when other frameworks like TensorFlow, for example, because everything has to be run inside a session. So another thing, if you want to identify why your code is slow, then you can just use any of the Python profilers. There's many tens of Python profilers, and you can conveniently find out which line is being slow. One of my favorites is Line Profiler, where it will show you line by line which line is being slow, and you can try to go optimize that. And then coming to compilation time, if you have ever used something like Theano, you know that if you start an experiment, it will take some time to start, like because it is compiling. But PyTorch is written for people who are very impatient. They don't want to wait for anything. So we don't have no compilation. Immediately as you start, PyTorch will just start the script. There's all the kernels that are compiled are pre-compiled and shipped to you. Coming to ecosystem, you can use, because PyTorch has this NumPy bridge, you can use any functions in SciPy or scikit-learn or all of these, and it's pretty easy to do so. One of the examples, it's probably going to be hard to read, but someone basically combined PyTorch with SciPy seamlessly, where part of their model is a neural network within PyTorch, and other parts are like going into SciPy. And they were doing this quadratic solver combined with the neural network. And we actually have a tutorial that shows you how to use SciPy with PyTorch's autograd engine. Another thing in the ecosystem is actually there's a model zoo. There's several popular models available to you, and it's just with the one line you can load the model from Amazon, and it is available to you in your program. Here's an example of someone from GitHub who took the entire PyTorch model zoo for computer vision, and they tested whether the models run with what accuracy they would have if you quantize the models to use lesser bits. So by default, all of these neural network models are trained in 32-bit float precision, but the experiment was if I reduce to 12 bits, 10 bits, 6 bits, how does the accuracy of the model change? And if you have a model zoo, trying something like this is very convenient. It's like just a few lines of code. Another thing that makes PyTorch convenient is that your code is always linearly flowing. There's no, to run one program, you don't jump from like one line that goes above somewhere in control flow and then comes back, because that's generally harder to debug. The programming model of PyTorch is basically very suited for writing late programs that flow linearly. And it's not something that's just unique to PyTorch, but it's the style of programming that we popularized. And PyTorch actually has one of the fastest implementations of such a programming model. Actually, that's it's 15 minutes left. I'll quickly go over some recent features of PyTorch. There's a distributed PyTorch that we introduced in 0.2, and it's you can train your model on multiple GPUs, multiple machines. We have trained them on thousands of GPUs at once, and it's very stable, it works. And you can also take higher order derivatives, so not just taking the first order gradients, but also like you can take the Hessian, or you can do like any order derivatives. And if you have a crazy idea, then you can use this feature. We also have broadcasting and advanced indexing, just like NumPy. It's a very convenient feature of NumPy that we've implemented. Another thing we have been building is a JIT compiler for PyTorch. So if you write your code and you enable the JIT, it will automatically be fused to be much faster. Just as an example of what generally why you see these benefits, is if you have something simple like this, where you're just adding two numbers and then adding a third number. If you write it as a NumPy program or a PyTorch program, the actual code that is run is one for loop will first add A and B, and then the output of that will be added to C. This is what you call a bandwidth-bound program, because the speed at which this program runs is how fast your system memory is, because the computation that is being done is just a single addition between A of I and B of I, and so it's not actually compute bound. If you do something like operator fusion, then you can transform this code into something like this, where you only load A and B into memory once and keep the result in the register, and then you just do the multiply with C in register and then put it in the result. And this is usually much faster because you're avoiding one full memory load. This is just one example of how fusion is helpful. So with our JIT compiler, we expect to do things like kernel fusion, some out-of-order execution, and also in the future automatically using as much compute as you have rather than you manually specifying. And the way we are implementing our JIT in the initial release is we have what we call a tracing JIT, where when the first time that you run your program, it will trace through all of the operations that are happening on your tensor, and in the subsequent time that you run the program, it won't actually run your Python function, it will actually run your trace that it has optimized. And so that's the conclusion. We released PyTorch earlier this year in January. There's a lot of users, and we would love it if you tried PyTorch and give us some feedback. Thank you. I could take some questions now.
Hi, I'm Danny, and I have been using PyTorch for months, but I want to know why PyTorch does not support Windows.
So actually, there's one guy in GitHub, Peter JC123. Mm-hmm. He is from Shanghai. He is maintaining the Windows port of PyTorch. Mm-hmm. We plan to support Windows starting the next major release, which is 0.4.
Oh, okay, thank you.
The reason we didn't support Windows is because none of us have Windows computer, so we don't know how to develop.
Hi. By the way, actually, I work on the PyTorch window for a long time, and yeah, so that works very well. So my question is, you just mentioned the JIT, right? So in which release or about when you'll be available?
So the JIT, right now we are giving it to some people to just test. The way we are doing this is we are trying to find the places where the JIT can be most effective, where we can give most speed ups. We are likely going to release the JIT in the next release, which is 0.4.
About when point four will be released?
0.4 will probably be February. Yeah,
Yeah,
absolutely.
Hi. Have you done benchmarking of JIT and compared to other frameworks like Café, TensorFlow?
Yeah, so actually our gold standard is if the cuDNN developers wrote the same code, then how fast would it be? We did look at TensorFlow XLA and Café, but the JIT is much faster than either of those because we do fusion, which they don't. Like XLA does some fusion, but it's like barely working. So we compared it with those, but we're not interested in that comparison because that's just not even that fast. Our JIT right now is in the limited set of things that we're doing, like LSTM fusion and stuff. It is looking to be close to cuDNN speed.
Okay. What is the extent of that question? I'm wondering, just-in-time compiler. So your main idea is to prevent the catch miss, to improve the
that is one of the ideas that I showcased, where we want to do a lot of in-register, and it's not even preventing cache misses. So if you have a tensor that is 100 MB, then it does not hold in cache either, right? So you're just trying to take it from being memory bound to compute bound. The other optimizations in the JIT we do are eliminating operations that are useless. Sometimes if you write a long sequence of operations, some of them are not needed to compute the final result. And we have a few more other tricks that we're doing as well.
Any other questions? There's some time before lunch break.
Okay. I guess no more questions. Thank you for listening, and thank you for not sleeping.
Let's thank Soumith again.